Thank you for inviting me to this meeting to talk about 75 years of graphical user interfaces, some of which I was present at. But before I would do that, let me thank colleagues who have helped with this talk. I always like to show them first because these acknowledgments often get lost at the end. So thanks to all of these folks, many of whom have been colleagues for quite a few years. And first, I'd like to ask the audience this question. What is the user interface for this conference? Think about it for a few seconds. I think this user interface is something much like what could have happened 100,000 years ago when we were all gathered around a campfire. Stories are the major thing that we're using, and that's the major thing I will use today. And this cave guy, Unterhorsen, would understand everything that I'm doing here. Now, let's say instead of 100,000 years ago, to help me in my efforts, we only go 60,000 years ago when the first cave paintings were used. And I'm going to show you pictures. So I'm essentially doing this in this conference. And I'm doing this to talk about inventions that required writing, but none of you will be reading much during this conference. And almost everything that we're talking about will be given in common sense terms rather than the writings of science. Now, we also have a problem in speaking about user interface in thinking about what is it that we're imitating or thinking the computer is like. We've used it as a vehicle. We sometimes think of it as a tool. We have agents. We think of it sometimes as something like a cloud utility, like electricity and water. We think of it as something to play with, something to do work on. And here's one that's more or less taken over these days is the Skinner box idea, where the rat gets a food pellet every time it hits a paddle. And just as with our social media today, the researchers years ago who were experimenting with rats found that an intermediate response, that is a random response, was much more powerful in getting the rat to keep on hitting the paddle. That's still in use today. We think of it as a communications device. We think of it perhaps as something like a book. We think of it as theater, a makerspace. Maybe it's our entire home these days. And the latest is some of us think of the computer as our best friend. Each requires something between us and the hardware of the computer, which I'll call a user interface. And I've forgotten a couple of things here. One is, how do we program it? For most of the existence of the computer, including today, people think of it programs as being like recipes in a cookbook. I think it's more like trying to run a very large city. It's much more complicated. And finally, there's the essence of the computer itself, which is something that deals with descriptions, and we can think of it as like a meta-medium. It's a medium who makes other media. And so this is a very difficult thing indeed. And so we should ask ourselves questions while I'm giving this talk. How much help is too much help? When is user-friendly actually unfriendly, and vice versa? We want to help the user learn and adjust to their forgetting, and the nature of the task vastly controls the interface design. Starting somewhat arbitrarily around 1950 here with Whirlwind, which, despite what you're looking at here, was a 16-bit wide computer and thus officially a mini computer. But we can see that Whirlwind back in 1950 was a whole floor of a building, and in its control room, it had a big display, and a device to point at the display. This was originally used to track planes and radar. In fact, in the middle of the decade, Whirlwind 2 was a system that was in concrete blockhouses. There were about 24 of them. And this is a football field for giving you a comparison of the size. They were all connected together by a network. And on the second floor, there were two very large computers of 50,000 vacuum tubes. And at the top floor, there were 100 to 150 of these plane tracking terminals, which were driven by these supercomputers of the day down below. John McCarthy took one look at them as he was consulting for IBM and came to a different conclusion. He said, someday every home will have one of these. And so he thought of it like a utility as we think of the cloud today, and made an interesting point. To work for most people rather than just a few, it will have to communicate in human common sense terms. And he was thinking of AI at the time, and we'll talk about that in a bit. Now, a couple of years later, the experimental research computer of this community was loaned to a single graduate student between 3 o'clock and 6 o'clock in the morning. This is the time when we say there was only one personal computer, when Ivan Sutherland got it early in the morning for a year in 1962. And if we go down through the racks of vacuum tubes of this computer, we see him at work. It looks like he's drawing something on a glass panel there. He's pushing buttons. He's clicking switches. And here's what he's doing. System is called Sketchpad, and he's drawing a flange here, but he's just drawing it as a sketch. And now we can point to the parts of the sketch, these lines, and say to the computer, make them either horizontal, whichever is closer, and it just straightened them all up to make them mutually perpendicular. And you can see this is the first system to have a clipping window. He's going to use the same trick here, say make these either horizontal or vertical. Notice they cling to the lines above and below them, so this makes them parallel. Now he's using these lines that he drew as guidelines to make dashed lines. You can see he's terminating the drawing by flicking his wrist there. That didn't last. Now he's got a hole in the flange. And the hole in the flange seems to really want a rivet. So again, we get to see how this works. He draws crossed lines here, and he wants the center of the top of the arc of the rivet to be on those crossed lines, both of them. And again, if he points to these and says, make these horizontal or vertical, whichever is closer, the drawing straightens up and Sketchpad solves the problem of how to make a rivet. And what he was working on was something we recognize from object-oriented programming, which is, that was a master drawing. And what he's got here is an instance of that master. We can see he can make it different size, different angles of rotation. Now he's going to get some more instances. And he says, whoops, I don't like those cross lines. So he goes to the master drawing and gets rid of them. And we see now that the instances have felt that. So they're all imitating the master as they're supposed to. And now he's showing us that any combination of drawings, he's got a combination of a rivet and a flange, can also be made into a master. And he can make instances of these. So what we've got here is something that's not, it was the forerunner of many thoughts about object-oriented programming, but it adds the idea of constraining the entire system. This is not incompatible with OOP, but it's only done in special cases still today, which is about 63 years later. And there are amenities in Sketchpad. For instance, once he starts a line, he doesn't have to be perfect with the way he draws the line. You can see he can have a path there, and the line will be a rubber band line. And the same with the arc of the circle, it will be rubber band circles. And there's a gravity field that helps the cursor find the lines. When he's close to the lines, the cursor will jump to the line. And you notice it was two-handed operation, has knobs for zooming, size, and rotation, has many other constraint solving properties. And the solution of the constraint is the closest one to the initial sketch. This allows the sketching towards a drawing automatically to work. Now notice these drawings here were also made by Sketchpad and plotted out on a plotter. And the thing that we see here are alphabetic characters. And how do we get those? And like this, because alphabetic characters are just instances of masters of these shapes, and that T looks a little bit like a rivet. So it gives us the idea, well, what if we made that T, master T, into a rivet shape, and what would that look like? And that would look just like this. So this system could make pretty much everything that it needed from these basic ideas on this supercomputer that was originally made in the 50s. And here's a close-up of the console, and we can see the display, which is about, the active area of this display is about 9 inches on a side, the light pen, buttons, the knobs for moving and zooming and rotating. And in case the computer crashes, he can call up help in order to get it going again. So what we should be really asking ourselves here is, was Ivan just trying to imitate what you can do with paper and pencil? And he had started out that way, but he realized that the constraint solver allowed him to do something much, much more important. So he's going to make that truss bridge that was on the screen. So here we have instances of the basic form. And he's going to open these up. And these numbers represent the error between what the constraint solver has to do to make the drawing hang together and the actual length of the line. And I even realized these errors could be thought of as tensions and compressions in the beams of the bridge. So now he's saying to this bottom line, go to the bottom, and it's pulling the bridge down. And you can see that there's both tensions and compressions required. Mostly, of course, tensions, because it's pulling, stretching things. And so what we actually have here is something much, much more important than CAD, which is the ability to also simulate the computer-aided design. So this is the forerunner of all of our CAD systems. And the Sketchpad caused a sensation when it happened in 1962. And another wonderful system that was originally done in 1962 was done on a much smaller machine, but also had a display. And that was the game called Space War. And it was the first multiplayer game also. Then, fortunately for computing research, the Pentagon decided to give this guy, who is a psychologist, J.C.R. Licklider, money left over from the space program to do computer science research in the 60s. And what he said was the destiny of computers is to become interactive intellectual amplifiers for all humans, pervasively networked worldwide. That was started one of the best funded and the most productive research programs in history. Here's a memo he wrote the next year, 1963, and notice it's for members and affiliates of the Intergalactic Computer Network. And what does that actually mean? Why did he do that? When they were asked him why did he call it the Intergalactic Computer Network, he said, well, engineers always give you the minimum, so I'm asking for I want a network that covers the entire planet, so I'm asking for an intergalactic one. When they scale that down, it will still cover the entire planet. And he made an important point in this memo, is that our main problem, if we make a really large network, will be learning to communicate with aliens. And he meant aliens in many different ways, as we'll see soon. And he pointed out that getting machines of different types to talk to each other, getting humans and machines to communicate with each other, and getting humans and humans to communicate through machines is all something like the problem of learning to communicate with aliens. So using this money in 1964, a group at Stanford Research Institute invented a really simple pointing device called the mouse. And a group at Rand Corporation down in Southern California invented a very capable, very complex pointing device called the Rand tablet. And in these two projects, we'll find two very different approaches to user interface that'll be of interest. And it turns out both groups were right, as is often the case when you have open-ended research. So the first system was called NLS. Doug Engelbart was the head of the project. And the basic way they looked at things was, we want to train new people to do things in new ways with a new system. So they wanted to do everything new to give us the maximum ability to use the power of the computer. And the people in Southern California looked at it differently. They said, we already have lots of analysts. We want to give them a system that will magnify what they've got. They are already analyzing things. Let's help them analyze them better. So let's look at this first system. So the Engelbart group, besides inventing the mouse, which is probably the least important of all the things that they did, had very big ideas about tools. So the first kind of system described in this 1962 document, which I urge you to read, had a 3 by 3 foot display. It had a light pen. The light pen was hung over the top of it. And they quickly moved to something else. But their idea about what they were doing was to give humans power. And they realized that power does not teach you how to use things. So if you give somebody a hammer, you can hammer nails with it, but it doesn't say, there's nothing about the hammer that says you shouldn't hammer your baby sister with it or hammer somebody you don't like with it. So they were quite worried about the fact that our tools don't really teach us how to use them wisely. And in fact, could actually give us rather bad habits and ways of thinking. And so they decided that you must insert education and training in between the human and the tool. And this is something that has not been done except in specialized fields. But the intention here was it just has to be done. It's like teaching kids about drugs and staying away from guns and stuff like that. It's a fundamental thing. And then if you've got enough education and training in there, you might be able to change the effect on the brain of the user and make it safer for them and everybody else to use new methods, new ways of representing things, and so forth. And they gave a big demo in 1968. That's where I was sitting. And here's what it looked like.
As I say, I'd like to go to produce, but I'd like to go to produce. They get big. I'd like to say one branch only. And you look just that low when I see it. Oh, I can say, I'd like to see one line only. I can see it. But there's another thing I can do. There's a root I said I have here. So here, I'm afraid I'll need different pictures of you. So here's what I do with a picture drawing capability. Here's a slight map. If I start from work, and here's the route I seem to have to go to pick up all the materials. And that's my plan for getting home tonight. But if I want to, I can say, the library, what am I supposed to pick up there? I can just point to that. Oh, I see, overdue books and all. Well, there was a statement there with that name on it. Go back. What am I supposed to pick up at the drugstore? I see, there's a, all right.
Well, we're all familiar with hyperlinking, and this is the first demo of it in public. But the Engelbart group had much bigger ideas because they realized that most things that affect the world are not done by single people, but by groups. And so they asked the really important question is, what does it mean to augment the collective intellect of collaborative groups? So they thought it would be something like this, where you're training the group now of trained people. And their solution to this problem was good enough that when they held meetings, even in the same room, they used this system to help collaborating with, because they were sharing the context. One of the things about the user interface on this was it was inherently shared with other users at the operating system level. And they also had some remote researchers. And so a typical meeting would look something like this.
I see it over like that. It leaves a corner up there, and I say, now, computer, do the automatic switching that'll bring in a camera picture from the camera mounted on his console, such as the camera mounted on mine is. Hi, Bill. That's great. Now we're connected audio. You can see my work. You can point at it. I can see your face, and we can talk. So let's do some collaborating.
Go off to a directive file and see what the directive is to get Roman numeral pages.
So the difference here between what I'm doing and what was being done back then was that Engelbart was able to collaborate with Bill Paxton here because they could both point to and drag and click on and work the system simultaneously. So a few limited systems today are starting to do that, but this was for the entire operating system. Anything that you did on it was shareable. So that's something we haven't come to yet. So now if we look at this other approach, how did the RAND people go about doing it? And there's this guy, Cliff Shaw, who wanted to augment the existing analysts at RAND in the early 60s. And he said, well, they already write, read, do mathematics. Can we get them to program in mathematics if we made the system nice enough that it felt friendly enough? So they had this old computer they were going to get rid of, and he said, well, give it to me and I'll try and do a system on it. And back then it was typewriter terminals, and they made special typewriters that typed in different colors and upper and lower case and so forth. And the answer was yes. This system was extremely pleasant to use. He wrote what is probably the best, earliest paper on user interface design and how you do it. I think everybody should read this paper. And the last sentence of it says, in this designer's view, the acceptance of an open shop computer system depends on the little things, the hundreds and hundreds of little things. And that is what eludes many user interface designers today. And I've found that there's a Japanese word to express how this system felt to use. Komorebi means the sun shining through the trees. I love this word. And that's how you felt when you knew you were going to be able to use the system in the afternoon. You were very happy at the thought you were even going to be able to touch it. So the second phase of this, Tom Ellis decided to go through the waste paper baskets at midnight in the offices of the RAND analysts to see how do they actually do their thing. And the answer is a lot of it was done through flow diagrams of various kinds, laying out systems and laying out procedures and so forth. And so when they invented the tablet, they invented it with a very nice way of producing free-form ink. And one of their researchers, Gabe Groner, was given the task of being able to recognize those characters. And here's an example of the system called Grail in operation. So first you see it's got very smooth drag and drop. No keyboard. We'll find out why in a second. Just like a paper. Can point on menu items. Here's what inking actually looks like. This again was one person on a huge mainframe. So he was erasing the line that connected them and it disappeared. He showed it, he wanted a box and it made one for him. Now it's recognizing his handwriting. Here's where modern day window size control came from, literally. And notice this is context sensitive, so it knows he wants an arrow here. Erase that line. Erase that guy, move it out of the way. First windows at Park were moved around this way. Make another box. And notice there's two little errors in the recognizer here. That one right there, and here the made an F instead of an N. But it's modeless, so he can correct it any time. This is the first modeless system. And there you go. Now, again, we should ask the question, is he just imitating paper here? Is this just expensive paper? And if you look at the top of the screen, you'll see the words stop, slow, and fast. And this is because these diagrams could actually be simulated. And so we can see the flow going through the diagrams, and you can follow the hyperlinks dynamically as it went through at any speed. So this is also not just a CAD idea, but a CAD sim idea, which is absolutely critical. Okay, so those are two systems that were very impressive in the late 60s. And another thing that was going on in the 60s here was John McCarthy again and Marvin Minsky were working on what was called AI back then, rather different than today. And John had had the idea that you would need to communicate with users in common sense terms. And a graduate student by the name of Warren Titleman, who's very important in user interface design, decided that if you're going to actually allow most people to interact with computers, you have to have something like undo. Undo will allow them to have the courage to do things and make mistakes because the system can always recover. You can have redo, you can have spelling correction, you can have advising and so forth. So his thesis was called Pilot, A Step Towards Man-Computer Symbiosis, and he later went to Park and worked on Interlisp. Okay, Licklider was still thinking about aliens, and he was starting to think of the ARPANET, which is the beginning of the internet. And so the question there is, what does it mean for computers of different types to communicate? He was thinking of humans and computers because that was the whole point of this research. He realized that even communicating in terms of common sense descriptions could be misunderstood. And the most interesting thing they came to was that we don't often understand our own minds. So even using the computer as a private communication device, we can be conflicted. So this general question of what does it mean to communicate was one of the gifts of the 60s. And one of the conclusions from it was the end user is not us. And this is true even if we are the end user, because of these internal conflicts we have. We don't understand exactly all the time why we're doing things. And to round out the 60s here, we have Seymour Papert starting to work with logo and children to include children in the larger group of users. And that got a number of people to think of, oh, the computer is not really, it's more than a tool. It has something to do, it's more like a book. It's something that children need to learn, particularly if it's helping them learn science and stuff, learn earlier in life than they would normally do it for tools. And that gave me this idea, which was, after meeting Seymour, I started thinking about, well, what would a computer for children be like? And it would have to be really portable. And there were flat screens displays starting to appear back then. So this is a cardboard model, and that cartoon I drew on the plane flying back from my first meeting with Seymour. In the 70s, I think of largely being about trying to invent the personal computer. The 60s were trying to invent personal computing, which you could do up to a point on a time-sharing terminal and a cloud. But the user interface needs for personal computing seemed to require a personal computer. You had to have a fair amount of computing power. And the personal computers would be hooked together by the Ethernet, which is also invented at PARC. So PARC was set up, the computing part at PARC was set up by Bob Taylor, who had been Licklider's deputy. And he brought from ARPA many of the ways that they had found to be successful in computing science research and made them into a more refined version at PARC. And two things we talk about particularly is that Moore's law means you can make a time machine. I'll explain what that means in a second, but the way we did things at PARC was to try and make computers of the future in the present. So we could, instead of working on a computer that was getting more and more obsolete as we worked on it, we were working on something that would be affordable in the computer in the future, but we could do it right now. Then the second main thing was to pay attention to who human beings really are, to try and understand human beings much better when designing systems for them, and especially the user interface. So we decided that systems should never have a hard failure, meaning you can't lose any work ever. You have to do whatever is necessary to always be able to recover some past state. And then the large decision made was, well, let's just build all of our own hardware and software, and we'll just live in the stuff. We won't use commercial hardware or software at all. We'll just live in our own mess and make it work. So here's how Moore's law works. The idea of the Dynabook was just a dream. It was not possible in 1968 or even in the 70s. But it was an idea, and we had handy this exponential progression of everything good was doubling every 18 months. So the idea is you take that idea out 30 years, which is 20 doublings, which is a factor of 1 million. And you ask the question of the future, wouldn't it be crazy if we couldn't do this 30 years from now? And for the Dynabook, the answer was, well, yeah, we should be able to do it with another factor of 1 million 30 years from now. So then you bring the idea back maybe halfway, 15 years in the future. And then if you have a sponsor, you decide, well, I can spend money because Moore's law is basically going to give me a Turing complete computer in every era. It's just going to be faster. It's going to have more capacity, but it's going to be able to compute the same things. And so by just spending money, I can make myself a computer of the 80s in the early 70s. And that's what the Alto there was. And that gives us some time to invent the new kinds of user interface and new kinds of software that it's going to use. And so 2 of these were of particular interest. Because this computer of the future was so fast for each user, we could do many user experiments. So here's what the Smalltalk user interface looked like in the mid-70s. You can see there are different fonts of different kinds there. There's a drawing system. You could make your own fonts, and there's a way of programming the system and so forth. And the other thing is that if you're willing to optimize the software of the future, you could write software as people would do it in the 80s. And this is a 2-window system that was one of the earliest versions of what became Microsoft Word. So what was being invented here was not just demos, but pretty much an entire industry. Now, what do we mean by paying attention to human beings? Well, we looked at the work of many psychologists and anthropologists. Jerome Brunner had many useful things to say, including that we have multiple ways of knowing the world. We know the world by manipulating it with our hands and our bodies. We know the world by seeing things in configuration, usually in terms of images or in soundscape images. And we have this special thing that's very powerful, but we still don't understand very well, which is how to describe things symbolically. And Brunner gave us a progression of learning that was very useful. He said, doing with images makes symbols, and that the progression of learning goes kind of in this direction, and that we needed to come up with user interface solutions that used all of those. And you saw in the past examples that some of them did all of these. And the contrast and compare idea of learning things made us think about, oh yeah, well, we don't want just one window, we want multiple windows. And because the screen is so small, but it has a bitmap, we can actually make them appear to overlap like papers on a desk. We looked at the work of Frank Smith, who said literacy is not just reading and writing, but there's a literature that establishes a threshold. It's not enough to be able to read a street sign. You have to be able to do the equivalent of reading real ideas and learning the ideas in their written form. And then the guru of Marshall McLuhan pointed out that media is its own user interface. So he asked the question, the most important question, we'll bring it up later. What happens to us when we learn a new medium of communication? Our brain has to change every time we learn something. And how is it going to change if we do this? And there's this complete contrast between what we can be aware of and what we can pay attention to. So we can be aware of about 100 things in our environment. So there's a wide angle way of thinking about things. But we can also only pay attention to a few things. And so we realize that user interface partly means helping the users manage their attention. There's going to be a lot of things to see, but we have to fix it so when they want to concentrate on something, they won't be too distracted. Now, of course, one of the experiments that we were doing to follow up on this Dynabook idea was, what can children do? So here's a movie of Marion Goldine, 12 years old, and what you're seeing here is the first application tool actually made by a child. She's not just drawing a tree here. She actually made this tool, which is a painting application, has different kinds of brushes. She's going to pick the dot here. So she made these menus with pictures in them and is using it to control her drawing. So that was a good sign. It's not when you have just users using things given to them by others. That's unfortunately most of the case today. But we found that most children could actually make their own tools. Now here's a child, also 12 years old, who is first using an adult tool and then modifying it.
Hello, I'm Jim Differding from Jordan Junior High School, and I'm going to show you how to create an animation on the Shazam Smalltalk animation system. First step is to create a movie. This movie will start with one frame. We give it the name Ball. I point at the menu command that creates a painting window.
See the iconic menus.
Then I can get a palette of paintbrushes and paint tones in order to draw a small ball.
So she's putting in a little reflective spot there.
Next, I show how to give the ball a bouncing movement. I move into the movie window, select the movement command, and show the ball the path I want it to follow.
So this is an imitation of Disney animation.
Now I need to step to the movie frame where the ball strikes the ground and replace the ball with a squash ball.
So she goes to the step icon. What she's doing here is she's exchanging that picture of the ball down there for a fresh, transparent cell. So you see there's nothing there at the bottom. Now she's going to overdraw. She has a transparent cell, so she's not touching that first drawing. She's going to overdraw it. And you can see the drawing is being inserted in to the animation as she does it. And it will look quite real when she puts in the specular spot. Now she's going to use the fact that the animation is going along to, while it's running.
Now I want to change all the round balls.
She decides to make a rabbit.
A different picture follows the path I defined earlier.
Okay, so that is her using an adult tool. But we found that kids around the age of 12 could program about 100 lines of code back around 1974, 75 or so. So they could write about 100, correlated very much with how much of an essay they could write at that age. But as with reading, they could read around 10 pages of adult code. And it turned out this whole animation system was less than 10 pages of small talk. And so this allowed them to find things that were maybe a little more complex than they would be able to think up by themselves, but to actually change them.
Now I have a jockey.
So here's a feature she added.
I can superimpose the jockey on the horse to make a racehorse. Now I can have the jockey and the horse run across the screen by making another program.
So this feature was a feature of combining two objects together to make a new kind of object, as we saw in Sketchpad, but it was done by a 12-year-old girl. Now, our actual progress in making user interface first was every part of this project. I had a genius partner by the name of Dan Ingalls, and we worked together on all parts of this. And basically, we did what Cliff Shaw at RAND said, which is working on the hundreds of things that are needed and finding out what they are. So these are different user interfaces over the years. In the lower left there, you can see what animation was like on the Alto. It was quite capable. And we finally got to around years 78 and 79, we got to a system that looked like this. This is actually the system that Steve Jobs saw. So this is there were 3 machines at Park that in those days, and you see we put in a character recognizer like Grail had, have iconic menus. Now, important thing to think about, here we see modern looking text selection, character recognizers being used there to flush, go to the center, flush right, flush left. Here's what the painting system turned into. Yeah, and while I'm paused here, I should point out that each of these, what look like desktops, are actually entire environments. This is something that you don't see still today. It's the workflow idea is you want to have multiple places to do projects. These were called projects. And you could bring any parts of the tool, of the Smalltalk tool, to all of the projects at once. They existed over time, so you could have 3 or 4 projects you're working on simultaneously. Each one was held separately. So here's another way of using this system, which is to do what we call an active essay. So this is about Marion's experience in doing her drawing system, but she's showing us a demo here. If you look at the lower left corner, in this actual essay, this is something I can't do in Keynote or PowerPoint. She's actually typing code. She says, Joe, grow by 100. And Joe is the name of that box, and so it gets big, and so forth. So an interesting thing about many of these early systems is they actually, in certain ways, were a bit better than what industry has given us today. Now, back to the communication as an extension of the gesture. The idea we had was when people are speaking, they're not just saying words, they're figuratively pointing into their thought cloud at things that they hope are in the other person's thought cloud. And we decided to take that literally. And so the idea here is what we want to put into the thought cloud is this user interface, which is in human terms. And we can even allow because we have a mouse or a pen, we can allow the user to point to things And the windows are how we keep different contexts together and compare and contrast. And everything is active. There are no modes. We can undo. We need to gesture. The icons are are more memorable than words. And then Brunner's maxim at the bottom. And so this is all basic Jerome Brunner here. And a special thing to call attention to is being able to do undo. And the Park GUI, as we see, was not the first GUI at all. It was the product of much work beforehand. One of the biggest differences in the Park GUI, and maybe why it's still being used today, is because many more sources of information, including from the theater, the arts, anthropology, linguistics, cognitive psychology, and so forth, were used besides computing to come up with it. Now, a really interesting thing is while this was going on, what we're kind of using today, the next version of the future is being worked on by Nicholas Negroponte at the Architecture Machine Group at MIT. And Nicholas and I were we were best friends, and we were on each other's advisory boards. So these guys were working, as you'd expect by architecture people, of systems you could live in. So the end of this room is a screen that's the size of the wall, and things are much more pictorial than the Park GUI.
Take me to the museum.
So voice commands.
Go to the map above and to the west of the calculator.
So you can see the point of attention is going to move here. There it goes.
I'd like to make a phone call, please.
So many of the tools in this system were done by using appliances that were around most people's homes. Another very important thing to think about is if you're using video right now, as we are, what kind of argument could we have? We could certainly have a friendly discussion. We could argue up to a point, but at some point, we might start getting angry and we would need eye contact. So this is the first system that ever tried for eye contact.
I'm nodding. Looks like it. It won't last forever. Belief in human beings and a belief in proper use of technology, which you're right, I think that's essential to the understanding.
So you can see it's a projection of a
I think that would tie in
form.
with the whole general notion of cybernetic feedback.
To me, what it does, but the possibility, human power, human imagination.
He's wearing something on his wrist that knows where his hand is in
The
space.
blue cruise ship
There.
east of the Bahamas.
So this
Make
is-
a yellow sailboat
There.
north of that. Create a green freighter
There.
east of the sailboat. Create a magenta trawler
There.
there.
So that was a very interesting system to think about because it showed many of the things that people are starting to do today and showed many of the limitations and powers of it. So here's a system by HP that uses the limited AI of today, but it's good enough to be able to tell where a person's looking. And so it can match up the person's gaze on the screen to the person looking at the screen. So it's modifying the image on the fly to make sure that they're always having eye contact. And this allows them to go into deeper matters than without it. So this is an important thing to think about when you're doing user interface. Then the 80s and the 90s were all commercialization. And so not a lot of really interesting things were done. Two exceptions were spreadsheets and HyperCard. HyperCard was especially important, and I'm sorry it's not around now. And I'll just throw in later work that we did with children when we were at Disney in the late 90s. So this system had very simple programming and was highly drag and drop. So in order to turn the car, we're dragging a tile here called wheels heading, and we're dropping it after car turn by. So the car is going to turn wherever the wheel is heading, and that allows us to steer the car with the steering wheel. And the power of this system was really simple programming and a very uniform, capable environment. So for instance, you could take that menu of commands on the right-hand side of the screen, and it's an object just like the car. And so you can get an iconic menu from it and rotate it in place. So everything in the system was built out of the same stuff. This turned out to be very successful. This system called eToys was the forerunner of Scratch. And just for the fun of it, I threw in another project that we did during this time, which was really communicating with aliens. And this is Coco, the gorilla that knew about 1,000 words of American Sign Language. And Coco was an unusual being because she existed somewhere between, I thought of her as more human than animal. And but she existed in a very amazing space in between. And so we got interested in this, and you see on the lower left here a Macintosh user interface that we did for Coco that gave her a voice. So she could sign, but her vocal cords weren't set up for speaking. So this allowed her to point to things, and the system would talk for her.
Nice. You're getting much better at this. Oh, I like that one. Visit good, Coco says. Love, visit good. That was.
So an important idea thing to mention here, and it's not really a fair comparison because she'd been doing American Sign Language her entire life, but in fact, she was much more comfortable with signing with her hands than she was in producing human speech, even though she could understand human speech. Now, I, of course, have to include Hiroshi Ishii in as a major user interface designer. I really loved the Clearboard thing, which you can see is superimposing, doing collaborative work by not just showing the work, but also showing the person you're collaborating with right on the screen behind there. And of course, Ishii was one of the pioneers of computing out in the real world. And I have to mention Brett Victor. His work would require more than an entire talk to explain. He is one of the biggest thinkers ever in user interface, and I think he's the major thinker today. I'll show you two things briefly that he's working on. I'll let him explain the first.
This is the Dynamicland website. Dynamicland is a nonprofit research lab creating a humane dynamic media. And what that means is a way for real people in the real world to explore ideas together, not just with words and pictures, but with computation. But for us, computation doesn't mean scrolling around in screens. It means working out in the real world with physical materials, putting computational programs onto ordinary physical objects. It means computation integrated into real world activities, timbers to test tubes. It means using our hands, like playing a card game, or like a board game, or arranging scale models, or building scale models. It means making use of physical effects, using physical tools, crafting physical tools. It means making use of space, spreading out, getting everything onto the table, or the kitchen counter, or the walls, or the floor, or the middle of the room. So it's computation like electric lighting, wherever people need to be, whatever stuff they need to work with.
Yeah, so this is a very important point. I made it in a small way before, but Brett is a big thinker. And our visual field is much larger. The world we live in is much larger than a screen. And so thinking about things in terms of screen-sized little patches of things is only part of what it works for books, because especially books that have words in them rather than pictures, but it works less well as you expand out into the world. You need a much larger thing to look at. So here's an example that he made with a high resolution printer. So this is about 1 meter by 2 meters. And he made it so that if you put it on a computer screen, there isn't enough resolution on the computer screen to see what's actually there. We need it to be of a certain size in order to understand what he's talking about. But basically what he's saying is seeing spaces are learning spaces, that you need to have places where you can learn about things that allow you to bring as many devices and people together as possible. So his example here is a NASA control room, where people have many consoles together, many people, shareable displays, personal displays, everything, in order to understand something really complicated like a space flight. And we have to ask that question of software companies. Do they have such a room for these complex software systems that they're doing that we're now can worry about because they're starting to affect the entire world? And I don't know of a company that has a place like this where they can look at the state of their system. And the questions you can ask are, where are we? What's been happening? What just happened? What's about to happen? What can we do? And we also need to ask these large questions about UI. So now I'm going to widen the scope of this talk to look at some larger issues. For example, one issue is an idea that's very useful comes up, like undo, and now it exists much less. And for example, if I try to use Control Z while I'm giving this presentation, whoops, that isn't what I wanted to have happen. And Keynote makes me go through the entire build here. So that isn't what I wanted to have happen. Here's where we were, but what about the back arrow? That should work. No, doesn't work. Whoops, that took away too much, so I have to build it up again. This is not a very good user interface. And in fact, I had to go online to find out how to do the thing. I have to go up and say shift back arrow, and it will take one away. Okay, shift back arrow. I have to remember that because it's not actually in the Keynote user interface. Help. And how about an iPhone? Well, it was supposed to be wave the iPhone and you'll get an undo, but most people don't know that. And in fact, for most people and most applications, it doesn't work at all because the application people have not implemented a response to shaking. So an iPad, that was another one. I couldn't find any friends of mine who knew how to do it. It's actually 3 fingers swipe to the left will do an undo. Is that crazy? And Siri, when asked about undo, didn't even know what it was. So I think this is a problem this is in the small here. This is just a user interface for a person, but we're getting into the situation where we really have to think about the need to be able to undo disasters. And so we ask the question is, should user interface designers be more of a central part of building systems? because in many cases, just as with security, you have to start with the UI design in order to wind up with one that's really usable. So we recently had the CrowdStrike outage, which has actually wound up killing a number of people because CrowdStrike is used in many hospitals, which were put out of commission for a while. And the problem here was they didn't have any way of getting the system back up quickly. They didn't have an undo for a relatively simple error that brought down hundreds and hundreds of hospital systems and grounded airplanes and so forth. So this is a really bad idea. And part of the reason this has happened is there's no Moore's law for software. Our software is very similar to what how it has been developed for the last 40 years or so. That is not good because the hardware has gotten much more capable. And there's an interesting question of legality. I claim that system level undos should be part of law. People who put out these large systems that other people depend on, there's a duty of care idea. And should the user interface designers warn users, this is like a carbon monoxide sensor in a kitchen. It's not an option, you have to have one. So I'm going to finish here by saying something about how inventions actually work. McLuhan pointed out that the automobile did not really replace the horseless carriage. It wasn't replacement in something that was slightly more efficient and so forth. It was actually a qualitative change of the world. And many of those changes brought by the automobile were not thought at all by people who were making them or buying them. So for example, here, the car has, in many places, more or less destroyed cities. This is Houston, Texas, from above. The world yearly traffic death from traffic accidents is 1.2 million, which is, if this was a disease or a war, it would be paid attention to. But in fact, nobody I talked to had any idea that the human race has decided that it's okay to sacrifice more than 1 million people a year in order to have automobiles. And in fact, in the United States, it is the #1 cause of death for children from birth until age 19. And then there are larger system problems like global warming and the climate. So here's a way of thinking about this, that human genetics has stayed relatively constant. That cave guy and I am about the same genetically. And human inventions, there was a place where we were able to invent inventing. And that produced a gap between our wisdom, which is not so easy to learn or come by, and what we could be clever about. So the cleverness went way up and produced this gap, which without any help at all from AI has put our planet at peril. And so we've in effect given a cave person a nuclear tipped Tomahawk missile instead of a spear, and he might get angry. So Einstein pointed out that the problem here is not being more clever in the way we have been being clever. We need to be clever and intelligent in qualitatively different and better ways. And keeping on what we're doing is his definition of insanity. So the way to think about AI here is not whether it's done well or poorly, and not whether it works well or it doesn't. It works for some things and it doesn't for others, or whether it's intrinsically good or bad. The big idea here is that we can't handle it without being able to come through with larger ways of thinking about things. And I found another Japanese word that expresses one of the places we could look. Somewhere in between is where it might be. Thank you very much. It's a pleasure to talk to you today.
はい、セッションムービーは以上となります。もうまさに GUI の歴史、それと起源という話で非常に面白いセッションでしたね。そんなですね、アラン・ケイさんとですね、ここから、ご登場いただいてですね、QA セッションに進んでいきたいというふうに思っています。はい、じゃあ早速いけますかね。早速いけますか。はい、じゃあ早速アランさんをお呼びしましょう。あ、Hello アラン。Nice to meet you. Hi. It's really, really interesting talk. So that's so good.
I'm afraid it was too long.
It's not
But
so
we got
long.
through it.
Yeah. I enjoy so much. And あと通訳の森川さんがいらっしゃるのかな。はい。
皆さん、こんにちは。本日通訳を担当します森川と申します。よろしくお願いします。
はい。本日は私が日本語で質問させていただいて、通訳の森川さんから英語に通訳していただいて、それをまた回答していただくという流れになっております。じゃあもう早速聞いちゃっても大丈夫ですかね。じゃあ聞いちゃいますね。私が何個か質問はもうすでに考えてきてはいるんですけど、もし聞きたいこととかあれば、またシャープポストデブでも募集はしておりますので、はい。じゃあまず一つ目の質問していきたいと思います。今回の GUI の中でですね、ダイナブックの構想っていうのが出てくるんですけど、その発想、どこから起源が来たのかなっていう、発想の最初の、考えた起源のところに着目して考えてました。最初にディスプレイパッドというのを実装し、その後マウスが生まれて、その後コンピューターっていうのはパーソナルになる。こういう発想のもとで GUI の歴史が進化してきたということが語られてたかなと思います。で、ダイナブック構想というのが1972年、こちらで生まれるんですけど、この発想、どのようなものから構想を得たのでしょうか。じゃあ森川さん、通訳お願いします。
はい。Okay, Alan-san, we would like to kick off with this question about the origin of the idea of Dynabooks. So in your session, I think we've touched upon the concept of the Dynabook on 1972, which evolved from display pads, mouse, and computers becoming more and more personal. But our question here is where that idea of the Dynabook originated from.
Well, I had worked on a desktop personal computer when I was in grad school, and one way of thinking about computers back then was that they were vehicles like cars, and children didn't learn how to drive until they became at least teenagers and stuff. But Seymour Papert was using computers to teach 10-year-olds advanced concepts in math. And when I saw that, I was a mathematician myself. When I saw that, I realized, wow, that's not a car. That's something you want to start children off early with. It's like a book. Start children reading early. And my particular interest was not so much mathematics, but in teaching children science, which is in the large, science is a way of thinking much better than humans are set up genetically to think. It's an invention of ways, and it's difficult to start children off with the basic idea of science, which is the world is not as it seems. And they've just been spending their first few years trying to understand the world as it seems. And if you do this too harshly, you will confuse them greatly. So our research was really about how to gradually add on to what children were learning about the world in a more natural way. We wanted to add on the unnatural, better thinking of science. So that turned out to take decades.
Alright. はい。まず前半 のご回答なんですけれども、そもそもアランさんは修士課程の頃から今日でデスクトップコンピューターと言われるようなデバイスに触られていたとのことなんですけれども、その頃のデスクトップコンピューターというのはもう車のような存在だったと。子供は大人にならないと車を運転しないのと同様に、子供は大人にならないと、コンピューターみたいな機械に触ることができなかったと。でそういった中で、シーモア・パパーツ博士ですねと一緒に研究をされる中で、数学の教育にこういったコンピューティングデバイスを使えないかということを構想され始めました。でこの研究を通じて子どもの学習という経験に少しずつコンピューティング技術を取り入れられていけないかということを考える中で、こういった構想が徐々に固まっていったというふうにここまでご回答いただいています。
ありがとうございます。
So example, an iPad looks like a Dynabook, but the purpose is completely different, right? So it's the purpose behind computing that really counts here.
なので、このコンピューティングを何に使うかという目的意識というものが根本から異なっていたと。かなり子どもだったり教育といったテーマがその背景に存在するものとして大きかったんですけれども、なのでそういった意味では今日でいう iPad みたいなものは構想としてはダイナブックに非常に近いんですけれども、結構その背景にある考え方や思想に違いがあったというふうに回答いただいてました。
ありがとうございます。まさに本のような存在だからダイナブックなんですね。で、さらに iPad とはもう完璧にそもそもその起源からして違うというところも含めてすごく面白い意見だったかなと思います。私のちょっともう一つ、他の質問をさせてください。特に子どもたちにですねフォーカスを当てて子どもたちでも扱えるものにしよう、そういった発想が随所に出てきたかなと思います。特にスクラッチの原型だったりとかそういったものもこの動画には出てくるようになっていて、ちなみになんですけど、なぜ子どもにフォーカスを当てたのでしょうか。大人と違って先入観がないからとかそういうことがあるんでしょうか。
One quick follow-up question we have here is that what was the reason that you focused on children when developing this idea? Was that because they have less prejudice against systems? What was your thinking behind this?
Well, it was actually because children grow up to be adults, and I didn't like the way adults were running the world. So
一言で言うと、大人が世の中を動かしている様子にあまり好意的な印象をアランさんが持っていなかったと。なので子供が将来の世界を作っていく中でどういうふうにコンピューターを使うのが考えるのが大事だというふうにおっしゃっています。
Democracies need a certain level of ability, for example, to argue without trying to win, of understanding how different civilizations work. It's children need to be brought up to be able to handle the idea of democracy.
はい、なので子どもたちが成長するにあたって、どのような形で民主主義と言われるようなシステムが動くのかということを異なる民族間の異なる考え方を理解する過程においても、そういったものを大事にしながら成長していってほしいというような思いが背景にあったようです。
なるほど。非常に面白い話ですね。もともとその子供がその成長していく過程の方にやっぱりすごく興味があって、で大人が、例えばどうやって勝つかとかそういうことに関してばかり興味を持っていることに対してはなんかむしろ面白いとあまり思ってなかったというところから、むしろ子供たちのところにフォーカスを当てて話を発展させていくというところが非常になんかそういった姿勢があったんだなというふうには面白かったなと思いました。じゃあ次もう一個質問したいんですけど、undo や redo これをちゃんと扱えるようにするという統一的な考え方が、このスライドの中に出てくると思うんですね。で、私はですね実はそのブラウザを使ったアプリケーションを開発するっていうことを結構専門にしていて、例えばその時に戻るとか進むといったこのボタンがちゃんと動くこと、これは結構かなり気にしている方ではあるんですけれども、おっしゃっている通り、OS であったりとかブラウザであったりとかがこう提供しているユーザー体験から、ちょっと違う動きをするアプリケーションって使うのが難しくなるかなというふうに思ってるんです。しかし一方でですねアプリケーションも結構多様化してきていて、 独自の進化で UI を作っているっていうところも多くなってるなというふうに感じています。この流れってちょっと歯止めを利かせること難しいんじゃないかなと思ったんですけど、アランさんどうお考えでしょうか？
All right, so our next question is around the concept of undo and redo. So Yosuke-san here mainly focuses on building applications on browsers. And more recently, more and more diverse applications have come along. And that divergence is leading to this difference between users, how users interact with different applications. So our question here is, when these independent applications evolve by themselves, what is your thought around this trend of them having different user interfaces and actions to get along with these applications?
Well, I think the user interface inventions that we did 50 years ago are just a small part of user interface. So we would hope to see new user interfaces come along. I think the center question here is, how learnable is a user interface? How much help is needed? How much exploration is allowed? And undo and redo are really interesting to think about, because the earliest ideas was just, if you make a mistake going along in a chain, you can back your way up. And the forerunner of Microsoft Word allowed you to undo every action, even in its first go around. But if you think about it, that isn't, you would like something a little more sophisticated, because in between the place where you want to undo back to, there might be something you want to keep. And if you start, right, so it means it's not just a set of links going forward and a set of links coming back. On the way back, you might say, oh, I want to keep this part, but I want to go back here. And that can't get too complicated, or it starts interfering with the users thinking about what they're trying to do. So I think a really great undo system in commercial computing is yet to be done. We've done many experiments on this, because it can't be too complicated, but it has to be a little more capable than 50 years ago. And I think you could make an overall environment, because undo is ultimately based on user actions, and if you required that the component software be able to do its own undo, I think you could capture what's going on there, and you could make a composite system that would allow you to make more experiments and have more learning happen by the user. I mean, one way for people to think about this is, a user interface is really a curriculum. It's not access to control. You're not getting the controls of a nuclear submarine here. You're actually getting a curriculum of things that are making you more powerful by the fact that you're learning how to use the system. So it's really a completely different way of thinking about it.
That's awesome. Thank you so much. はい、まずユーザーインターフェースに関して50年前にアランさんが開発されていたようなものっていうのは、現在で使われているユーザーインターフェースの極めて部分的なものであったと。で、そういった中で新しいユーザーインターフェースがどんどん出てきていること自体は非常に興味深い現象だというふうにおっしゃっています。ここで重要になってくるのがユーザーインターフェースの取得しやすさ といった観点から我々が開発を行っていくことで、例えば、例として挙げていただいたundo、redo に関しては、初期のアイディアとしては、もうユーザーがそのコンピューターに対して行う操作というのは単なる操作の連鎖であったと。で、それを一段階戻すというような単純な考え方が当時にはあったけれども、現代におけるもう少し洗練されたアプリであったりですとか、複雑化したシステムにおいては、もう少しその間に保持したい操作があったりだとか、スライドの中でもご紹介いただいたような、もう少し間が必要なケースが出てくるかもしれないというようなことをおっしゃっています。そういった意味で、商用コンピューティングの世界における優れた取り消しのシステムというのは、さらに発展の余地があるのではないかというお話と、それから、もう少し俯瞰した観点からのお話もいただいたんですけれども、ユーザーの操作というのはコンポーネントソフトウェアの組み合わせによって現代において行われているので、もう少し UI がそのユーザーをエンパワーする、それぞれのコンポーネントソフトウェアをうまく活用して、全体の環境をうまく操作することができるためのカリキュラムのような存在で UI はあるべきだと、ユーザーに学習の機会も与えながら機能を提供する、そういった両面の考え方が必要になるというようなお話をいただきました。
ありがとうございます。まさに先生の講演からもあった通り、ユーザーインターフェースというのは一種学習の機会でもあるというお話だと思うんですよね。で、その学習の機会を得るにあたって、複雑多様化してしまったundo だったり redo だったりの基本的な操作が多様化してしまうことで、それが学びの機会、学習の機会を奪っちゃうっていう経験になるんじゃないかと、そういうことを危惧されているのかなというふうに思いました。その上で私もちょっとかなりその意見にはかなり賛成な方ではあるので、我々のような、エンジニアがある程度規律を保っていくっていうところは必要なのかなと。一方で今のお話にあった通り、商用業の、アプリケーションっていうのはもっと高度に進化しているので、今だったらもっと優れたタスクの取り消しだったりタスクのやり直しっていうのができるような機会っていうのが得られるんじゃないかというのはおっしゃる通りかなと思いました。ちなみにですね、本当は6時までなんですよ。なんですが結構長引いているのと、あとですね、質問がたくさん来てるんですけど、これちなみに全部あれですか一個も無理はい、時間がだいぶ押してるとのことですいませんが、ちょっと問いは立てたいんですけど、ごめんなさい、できないので、最後に僕の質問だけ1個だけ聞いてもいいですか。はい。じゃあ、最後にすいません、僕の質問だけ1つだけ。between さんが大事だという最後の言葉、こちら私の方では重く受け止めました。予期せぬ質的変化、こちらをどう見極めるべきかというところに帰結するのかなというふうに思っています。私にはそれをどうやって質的変化を見極めるかというところで、多角的にいかにものを見るかっていうところだったり、解像度を変えて粗く見たり細かく見たりするレンズっていうものが両方必要なんじゃないかなというふうに思いました。同じ次元で見るだけじゃなくて、立ち止まって別な角度から見たり、一旦全体などの視点を持つとか、そういったことですね。そういうのを得るために、そういういろんな見識を深めるとかやった方がいいかなと思うんですけど、そういったことに対してどうお考えでしょうかという。はい。すいません。お願いします。
はい。Okay, since our time is approaching, this is going to be our final question from Yosuke-san. So, at the last part of your presentation, you've described the concept of the Japanese kanji ma, in between. And in this context, we would like to discuss a little about how we should react to unexpected qualitative changes surrounding us. So Yosuke-san mentioned that it's important to view things from multiple angles, observe our surroundings by changing resolutions in a granular scale to a more higher level, and confirm things through different lenses. But what is your opinion on how we should discern unexpected changes surrounding us?
Well, it's a bit of all of the above. Let's do this interleaved. It's a bit of all of the above.
すべての事象を少しずつ俯瞰的に観察することは大事だとおっしゃっています。
But another way of looking at it is we can't learn how to see until we admit we are blind.
自分たちが盲目であるということにある程度自覚的でないと、自分の周りで起こっている事象を正確には捉えられない。
So that's kind of what happened with science. We
科
were
学
rendered effectively blind by our genetics.
科学の発展においても、自分たちが何を知らないかということについて知ることが非常に科学の発展にもこれまで重要になってきたと。
Another way to think about it is problem finding is more important than problem solving.
課題を発見することが課題を解決することそのものよりも大事である。
Because, and unfortunately, all we're taught in school and rewarded for is problem solving.
学校での教育だったり、その後の経験においても課題を解決することの方が、褒められたり称賛されがちだが、実際には課題を設定することの方が大事である。
And the other way to think about it is if you start picking problems out of the present, you're cutting off a lot of the future.
少し違った観点からのお話では、現在の状況から課題を設定しようとすると、非常に限られた課題しか設定できない。必ず未来についても考えながら課題を設定するべきだと。
Yeah, so I'll end with this last idea, which is from McLuhan. He pointed out about the Industrial Revolution that
この考え方はマクルーハン氏の考え方とも一致していて、産業革命の中でどのように課題を作っていくか、課題を設定していくかということが彼のテーマでもありました。
One way of expressing his insight was the Industrial Revolution is making lots of things for low cost and being able to easily distribute them. But what you're accepting from the Industrial Revolution is just usually an item, like an automobile or a television set. But he pointed out when you're accepting that item, what you're actually bringing into your life is an entirely new culture that's will stay completely invisible until it kills you.
産業革命においても、自動車だったり物的な変化に我々は注目しがちなんですけれども、本当に重要で考えるべきは、それが私たちの生活の質をどのように考えたということで、対外にしてこういった事象は我々を実際に、死に追いやるようなことがない限り、あまり我々はそれに自覚的になることが少ないですと。
Yeah, for example, Americans thought when they were buying a television set they were getting a little movie. But what they got was a completely different way of looking at things that changed what they considered to be normal behavior. And America is now living through a reality television show.
アメリカ人が初めてテレビジョンを手にしたときは、新たに
tolerate bad behavior. And guess what? The star of the reality television show is now the president of the US. That is McLuhan 101.
アメリカで起こった事象というのはかなりマクルーハン氏が考えていた内容に近しいということで、例えばアメリカ人の方が初めてテレビを購入したときは、新たなビデオテープを買ってきて家で鑑賞するっていうような発想がもともとあったんですけれども、実際に起こったこととしては、アメリカ人が考えるそのあり方そのものも変えてしまったと。リアリティショーを観察するような、例えば直近の大統領選であったりですとか、それに伴う人々の考え方の変化をとってみても、これは完全に人間の考え方だったり行動規範というものを変えてしまいました。
はい、なるほど。 ありがとうございます。はい、そうですね。ちょっとこう今のお話もものすごく面白かったって言うんですけど、まとめさせていただくと、まずその知らないことを知るっていう、その無知の知ってやつだと思うんですけど、知らないことをいかに知っておくかっていうのと、現在起きてること、これを疑って未来っていうのが何なのかっていうのをもうゼロベースで考えていったりとかする想像力も含めたところが必要なんだというお話。それを踏まえた上で、いろんな多角的な視野で見た上で、今起きていることっていうのを見つめ直しましょうって、そういったお話だったかなと思います。多分すごくいろんな造形が深い話なので、僕がまとめたっていいのかどうかわからないんですけど、今のお話がすごく、僕の中ではしっくりきました。はい。じゃあ、この辺りで一旦15分オーバーしましたね。はい。というところで、非常にもうあと何分切ってもいいんですけど、この辺りで一旦名残惜しいですが、時間になりますので、最後にアラン氏から、視聴者の皆様に一言だけメッセージをいただいてもよろしいでしょうか。はい。
Okay, thank you, Alan, for all your remarks. Before we close up this section, could you please give our audiences here your wrapping up comments?
Well, my wrapping up comments is have a great kampai.
最後に良い日本は
I miss most about visiting. I've visited Japan many times and enjoyed doing things there, and I love the spirit of the kampai. So, kampai.
乾杯。
乾杯。Thank you,
乾
Alan
杯し
さん。
ましょうでした。
日本に何回か訪れて乾杯の文化が非常に懐かしいということで、皆さんに最後乾杯という言葉で締めくくっていただきました。
ありがとうございます。本当にありがとうございました。以上でセッションを終了させていただきます。Thank you, Alan. Thank you. 乾杯。